Welcome back, chemists. In this video, we're going to explore redox reactions further, where we talk about balancing using the half reaction method. And the part that I'm most excited to share with you is a discussion a little bit about particle diagrams. So at the end of this video, you should be able to balance redox reactions using the half reaction method, and then construct a model to illustrate what occurs on the particle level during a redox reaction. So let's quickly review. So yesterday, we examined a reaction that looks something like this. I believe this was on your homework worksheet. So if we were to look at the oxidation half reaction, it would look something like that. Notice copper goes from a 0 to a 2 plus for the oxidation state, and then 2 electrons are what are lost. For the reduction half reaction, notice that silver goes from 1 plus to now 0. So then we have to indicate that 1 electron was gained. So at this point, we've identified that a loss of electrons is oxidation, a gain of electrons is reduction. So now I'm going to ask you to engage with a simulation to understand a little bit more about the reaction. So to do this, you want to click on Activity 1, which corresponds to various solutions. Choose the experimental setup that will match the reaction that we were just discussing, and then click the Continue button to see the molecular scale to answer the questions. Hopefully you took some time to examine the simulation. Now we're going to make sure that you're comfortable with the answers to these questions. So the first question, question 4, said, what evidence from the animation tells you this is in fact a redox reaction? So just by the fact that one substance is losing electrons and another substance is gaining them, that tells you that this is a redox reaction. The particle diagram was also very important here because you will be expected to construct your own particle models. So you're expected to include the reactants and the movement of electrons in this model. So remember the reactants was solid copper. So I'm going to indicate with a little Cu, that's the symbol for copper. It's also brown. And then notice I do show it so that the atoms are touching each other to indicate it is a solid. It's put in a solution of silver nitrate. So I'm including the silver ions because it is aqueous. However, I'm not including the nitrate ions because those are spectators. You were also expected to include the movement of electrons. So in the animation, you saw that one electron was transferred to one silver ion, and then another electron from the same copper atom was transferred to another silver ion. So notice that copper was losing 2 electrons, and then two individual silver ions were gaining those 2 electrons. Now it asks you to include 2 macroscopic observations above the beaker. So on your paper, you should have written that the solution changed from colorless to a light blue. And then you should have written something about a white solid or some sort of solid formed on the copper metal. Those are examples of macroscopic observations. Now, in number 7, this is very important. This is what really the lesson is going to emphasize today. It says, explain the difference in the stoichiometry of the half reactions you wrote and what is shown in the simulation. Why does this make sense? So notice below the beaker, we have the 2 half reactions that we originally wrote, right? Right when we started this lesson, this is what it looked like. But the simulation, you actually saw something different. In the sim, you actually saw 2 silver ions instead of just 1. So why does this make sense? Well, hopefully you're realizing now that if copper is losing 2 electrons, that means that the number of electrons lost has to equal the number of electrons gained by the other substance. So the reduction half reaction shows only one electron being gained by the silver ion. We know that the copper must lose 2 electrons to form Cu2+, so 2 silver atoms are necessary to accept both electrons. Okay, so now we'll take what we learned in the sim and apply it to balancing. As we've mentioned, to balance redox reactions, we're going to use something called the half reaction method. So we're going to build on what we learned yesterday. So as practiced yesterday, elements that are oxidized or reduced are going to be identified, and then we will separate these into half reactions, one involving oxidation and the other reduction. To balance the equation, the electrons lost in the oxidation half reaction must be equal to the electrons gained in the reduction. So for example, from the simulation, these were our 2 individual half reactions. We note that the electrons lost by the copper is 2, but there's only 1 electron gained by the silver. So what that means is we have to multiply the entire half reaction of the silver times 2. So what you'll do is you'll then rewrite both equations. Notice how I put the arrows on top of each other. It makes it so much easier. You can cross out those 2 electrons. They cancel out on either side. And what you're left with is the balanced net ionic equation for this reaction. Notice in this case, we are still balanced for mass and charge, right? There's 2 silver on the left, 2 silver on the right, 1 copper, 1 copper. Notice on the left-hand side, the 2 times the 1 plus, that's a positive 2 charge. And on the right-hand side, the copper has a 2 plus charge. So we are balanced for mass and charge, and we should expect to see this every single time we have our balanced equation. So let's try another example from scratch here. So it says balance the equation by using, again, half reactions. First thing you're going to do is always assign those oxidation numbers. That helps us to be able to identify what's being oxidized and what's being reduced. So in this case, we can see that the aluminum is going from aluminum with a 0 to now a 3 plus. So that means that 3 electrons are going to be lost here. We can see that our hydrogen is going from 1 plus to 0, and so that's going to be reduced here. Notice that in this case, the electrons lost does not equal the electrons gained. So the common number that both 3 and 2 go into would be 6. So that means they're going to multiply the half reaction at the top by 2 in order to get 6 electrons. And then the bottom half reaction is going to be multiplied by 3 in order to get 6 electrons. And this will ensure that electrons lost equals electrons gained. So now when I rewrite each half reaction, I then can cancel out my electrons. And then my balanced net ionic equation still incorporates the use of being balanced for mass and charge, right? You can add it up yourself. You can very clearly see that we're balanced for mass, we're balanced for charge, and this is our balanced net ionic equation. All right, chemists, I hope this video was helpful in understanding how to draw particle diagrams and balance via half reactions. You're going to have a lot of practice with this in class. Thank you so much for watching.